A photon creates, so here's this little photon going along, and then it has to pass near a nucleus, because a nucleus, in order for this to happen, it's got to conserve both energy and momentum, right? So it has to actually pass near a nucleus, because the nucleus will sort of carry off some of the momentum, which we really don't get into the energy momentum relationship, so we're not going to know why that is. This is just one of those esoteric things that IB expects you to just kind of memorize, but not really know the reason for. Okay, but anyway, and it can do this, by the way, near electrons. It happens every now and then, right? Any mass, anything that has rest mass that can carry away momentum. And basically, the energy. This is just like the photoelectric effect, right? The energy of the photon, right? Energy of the photon energy. We'll switch those of the. The energy of the photon turns into energy to create the mass. Energy to create mass. And then what's left over, and by the way, it's always a pair and a matter pair and an antimatter pair, right? So in this case, this is matter, the positron is antimatter, right? So it's energy to create the mass, right? Plus whatever's left over turns into the kinetic energy of those particles. Okay. The energy to create the mass is twice whatever the rest mass is, right? But do this in MeV. That's the key, is look it up. Don't do kilograms. I mean, you could do kilograms, and then you could, multiply by mc squared and get the joules, and then you could, divide by 1.602 times 10 to the, but don't do that. Just look it up in MeV, right? The kinetic energy will also need to be in MeV. So, and then the kinetic energy is going to be divided evenly between them, okay? Because they're going to fly off and they're going to need to conserve momentum, okay? So let's see. Let's figure this out. So the photon energy, we're going to create an electron-positron pair, right? If you look at your data packet, you'll see that the rest mass of an electron and also the rest mass of a positron, right? The antimatter particle has the same mass as 0.511 MeV. So you're going to go 2 times, and that's MeV, right? And then they each have 0.211 MeV of kinetic energy, so 2 of those. This is the total bill. Right, so the total photon energy here is, let's figure this out, 2 times 0.511 plus 2 times, a lot of 1s here, look out, all right, 1.444, okay, 1.444 MeV, there we go, right, okay, so now the question is, what is the wavelength of that photon, right? And I've saved this space here to determine that, right? So we're going to go, what are we going to do? We're going to say lambda is hc over E, right? The energy is, the photon energy is 1.444 times 10 to the 6th electron volts, right? Because remember, M is times 10 to the 6th, right? So don't forget that. That's this is the most important part to not being off by a factor of 1,000,000, right? Okay, so MeV, that's the energy of this photon. Holy cow, right? So then we're just going to go 6.626 E minus 34. That's joule seconds, right? 3E8 meters per second, right? And then our energy is 1.444 E6, and this is electron volts, right? And then we have to turn this energy into joules, 1.602 E minus 19th, and this is joules per electron volt, right? And now let's just have that. Let's see, 6.626 E minus 34 times 3 E8. Those pre-multiplied HCs in the front of the data packet are looking awfully good. All right, here we go. Okay, let's see. Okay, and then I'm going to divide by 1.444 E6 and also divide by 1.602 E. And this is a photon unlike any we've seen. So this is a killer photon, right? I'm getting 8.5929 times 10 to the minus 13th meters. So forget nanometers, baby. This thing is so energetic that it creates matter, which this is, of course, how all matter was created, right? Is that matter is basically a resonant form for energy. It can resonate at certain modes. And photons with this much energy can go back and forth between being matter and whatever, right? So if a photon's got this much energy, it can create matter with this much kinetic energy. And right after the Big Bang, of course, this is a lot of photons with this much energy existed. And so matter was being created and annihilated and created. Anyway, that's a very cool thing. All right, that's that. I'm going to just sort of, for a second here, I'm going to find that. Let's go look at the. So if you're done, I mean, this is it, right? I'm going to go look at the. Let's go here at the data packet, and let's find that. The HC part. Let's see. Oh, I already went by it. There it is. Look at that. All right, let's zoom in a little bit here. Okay. Yeah, look at this. HC is 1.24 times 10 to the minus 6 electron volt meters. Okay, so let me just write that 1.24 E minus 6th. All right, I'll do that, and then let's go back to this thing, right? And just for fun, let's wavelength is HC over E, right? Okay, so let's use the HC. This is electron volt meters, right? And so let's have at this, right? So 1.24 divided by, and then we knew our energy was 1.444 times 10 to the 6th electron volts. Now this should work, right? We should get just meters from this. So divided by 444 E 6, and I get 8.587, so times 10 to the minus 13th. So that's really, with 3 sig figs, it's the same number. That's kind of cool, right? I mean, that saves you typing in 6.626 times 10 to the minus 34th times. So this basically is HC over E is what it is, really. So it saves you typing in all of those numbers. You can just use this. That's kind of cool.